Greetings and welcome to a new video. In this video we will discuss a very interesting situation, which is the frequency response of a BJT amplifier. We will see how we can determine the low frequency cutoff and also the gain of this circuit, having this coupling capacitors and the bypass capacitor in this circuit. Of course, we will see everything step by step clearly in our discussion, and we will also verify these in SPICE simulations. Alright, let's look at our example. We have the following circuit given. We have the BJT here, Q1, which has the following parameters. The VBE, which is the base to emitter voltage, is assumed to be 700 millivolts. The beta is 290, and we assume the early voltage is infinite. And we have the given the resistors here, R1, R2, and Ri. Those are shown here, and also the RC, the collector resistor and emitter resistor is also shown here. And we have a load. And we have three capacitors, C1, C2, 100 nanofarads or 0.1 microfarads. We have 1 microfarads, and we have the C, which is 10 microfarads. And the power supply VCC, so we have only one power supply in this circuit. Now, what are the questions? The questions are the following. We'd like to determine the maximum voltage gain, which is given here as AV max. And we'd like to determine the lower cutoff frequency for this circuit. In this case, we have the capacitor, so that will be the situation where we can use the frequency analysis in more detail here. Okay, let's see that in more detail. First, we discuss the DC analysis, because the information from here will be used in our AC analysis and for our frequency response later. Now, we begin also by assuming that the transistor, the BJT Q1, is working or operating in the linear region or active region. So we assume that. We will check that, of course, afterwards. And that means we can use the following equation or formula. IC, which is this collector current, is the beta here times the IB, which is then flowing here. It is the base current. This is only valid if you're in the linear region. So for the DC analysis, we assume that the capacitors are perfectly open, so we lose this part. We also lose this part because the capacitor C2 is also open, so you don't have this resistor RL. And since this is also open, so you only have this mid part of this circuit, and that's actually shown here. Now you also see the labels for the currents and also the VCE, and I also labeled here this point B, which is the base node. Now what I will do next is convert this circuit into the Thevenin equivalent circuit. Why? Because that will allow us a more convenient way to calculate the required values for this next step. So I use the R1 and R2 to calculate the R Thevenin. That will be discussed in more detail shortly. And the Thevenin voltage, VTH, will be also calculated using the two resistors and the VCC. So the Thevenin equivalent circuit at node B here is then having the Thevenin resistance, which is this RTH, that is just a parallel combination of these two resistors. So you actually look back and you also disable the VCC, so it means this is then shorted. That means you see effectively R1 and R2 parallel. And if you now do the math here, you get here 15 kilo ohms effective, so this is 15 kilo ohms. And the Thevenin voltage is actually calculating here this voltage using voltage divider. That means R2 over R1 plus R2 times VCC, and the values are shown here, so that will result in 6.75 volts. So this is then 6.75 volts, and this is 15 kilo ohms. And now we can apply here the nice formulas for the Kirchhoff's voltage law and continue further. So that's actually what we do here. So in this part, at the input, I will apply the KVL. So I say Thevenin voltage is equal to the voltage across the Thevenin resistance plus the voltage VBE and the voltage across the RE. That's all shown here. We know the emitter current is equal to the base current and the collector current. So we can add them up. So effectively you can also say beta plus 1 times the IB. That's effectively actually the emitter current in terms of the base current. I will take this and put it in here. That's actually shown here. So I have now one equation where you see the IB here and other parameters. So what I can do, I can now collect the parameters for IB together. So you see the RTH and this RE times beta plus 1. And that's shown here. In order to now express the IB in terms of the other parameters, I can do the following. So I do VTH minus the VBE divided by this term, which is actually shown here. So you have now a nice formula where you can calculate your DC base current, having the Thevenin voltage, the Thevenin resistors, and also the other parameters from the circuit. Alright, let's bring this here and also use that for our next step, because the base current can be now calculated. 6.75 here, minus 0.7, which is this 700 millivolts, divided by this 15,000 plus 800 times 291 actually. That is 24.41 microamps. Now for the collector current, we only use this beta times the base current. That is assuming the linear region of operation. That is now shown here. And that will result in 7.08 milliamps. And the collector current is then the emitter current is then beta plus 1 times the base current. And that's shown here. So that is actually these two together effectively. So that will be then 7.105 milliamps. Now let's also verify now that this is indeed working in the linear region. So we first do the Kirchhoff's voltage law at the output loop. That's actually again looking at this circuit. So I will determine the voltage VCE. So you see VCC is equal to the voltage across RC plus the voltage VCE plus the voltage across the RE. That's all shown here. We know actually these currents, the collector and the emitter current, and also the VCE can be now recalculated because the rest is also known. So let's express the VCE like so. So VCC minus the voltage across the RC and voltage across the RE. So that's actually all here, and that will result in 5.235 volts. This is much larger than the 0.2 volts we need minimum in order to stay in the linear region. So this is actually also verified. We can also do it in an alternative way. This is also possible. You can look at the voltage at node C and also at node B, and then look at the condition that the node voltage C must be larger than the node voltage B. That's what you can do. So node voltage C is actually the VCC minus the voltage across the resistor RC. That's actually shown here. So it will result in 10.92 volts. And the voltage at node B is this voltage VBE plus the voltage across RE. That's shown here. So 0.7 plus 800 times the emitter current. That will result in 6.384. So this is indeed true. So the collector voltage is indeed larger than the base voltage. So we actually also come here to the point that the BJT is operating in the active or linear region for this case. So we can assume, or we can say our assumption is correct. All right, let's go to the next step, which is our AC analysis, and we bring our circuits for this situation. Now we assume in the AC analysis that all the capacitors are perfectly shorted. That will be not the case when we do the lower cutoff frequency analysis. That will be done shortly. So this is a short, that will be a short, that will be a short. So we actually see here, and also the DC sources and the currents are disabled. So for the DC voltage source will be then a 0. So this is also ground. That's why you see this RC here to ground and also the RL together actually now effectively parallel, because this part is also shorted. We also see the R1 is going to ground and R2 is also going to ground. So again, effectively in parallel. And we also see this. This part here, R pi and the GMV pi, that is the model of the BJT. Since we do not have, or the early voltage is infinite, we don't have this RO here, which is between the collector and the emitter. That resistor is infinite. So we can, let's say, neglect that. And we can continue now and discuss how we can determine the voltage gain. So R pi first. How do we determine R pi? That is then given by this formula, which is the thermal voltage divided by the DC base current. We know the DC base current from the DC analysis, so we can substitute here the values. By the way, the thermal voltage is 26 millivolts for the room temperature. It can change depending on the temperature, so it will go up if the temperature goes up. But in this case, we take room temperature, which is then 26 millivolts. And that is then approximately here 1065 ohms for our R pi. So this resistor is 1065 ohms. Now we also need this GM, which is given by DC collector current over this thermal voltage, and that is using this DC collector current, which is determined in the DC analysis. Substitute this in the formula, you get here 0.2723, and the units are here Siemens and not ohms, so it is actually a conductance. So you have the parameters here, and we can also designate here this node, which is then this node voltage VB. And we can now continue in order to calculate our voltage gain. So the voltage gain we want is the VO over VI. So that is the voltage gain we are looking for. And that can be also separated in two parts, which is actually the VB over VI. That's actually this part first. And then going from here to the output, which is then V over VB. You see actually the VB can be then divided out and you get exactly V over VI back. So this is more convenient and easier to do instead of directly V over VI. I first make here the impedance looking in the base node, so I call it ZIB. So I would like to determine first what is the impedance I am looking at if I look into the base node. So I call that ZI input in the base. That's effectively R1 in parallel with R2, in parallel actually with R pi, because this is also grounded. So we can say this, and if I now want to calculate that, I can say 1 over the ZIB is equal to 1 over R1 plus 1 over R2 plus 1 over R pi. And I have now R pi just calculated, and R1 and R2 is given here. So we can calculate that, just substitute here the values, and you get here 1 over the ZIB is then this much. It's then approximately 1.0057 times 10 to the power minus 3. So ZIB is then 1 over that, which is then 994.3 ohms. So I see this resistor looking in the base effectively. So I can then apply here the voltage divider rule actually, so I can say VB over VI is ZIB over the RI plus ZIB. And I can also say the VO is minus GM, why minus GM? Because this current is going that way. And in order to calculate the current here, or the voltage here I should say, is this resistor effectively, which is the parallel combination of the RC and RL, times the current flowing here from this top node to ground, which is the minus, the opposite of this current. That's why we have this minus. So this is the current, and this is the effective resistor. And that resistor is then actually calculated here. So 1000 and 2000, or 1 kilo ohm and 2 kilo ohm effectively will then result in 666.7 ohms. And GM we know, but we can also rewrite this. So we can say VO over V pi is minus GM, and then again this effective RC parallel with RL. But we know V pi is VB. Look at that, because the VB, this node voltage going to ground, is exact same as V pi. So we can also replace this V pi by VB. And then we have the following using this expression. We can say ZIB over RI plus ZIB, that's the first part, this one, times this minus GM and this RC and RL in parallel. Now this is the formula we can use to calculate now the gain, the voltage gain. Now which is then here in this case, substitute here the values. We also know this GM, everything is substituted, and that will result in a minus 165 as the gain, which is again this minus, which is inverted, and we have that in dB as 44.3 dBs. All right, that's the first part. Let's now go to the lower cutoff frequency analysis. For that we use a small signal circuit, as we have done it before for this question A, but now we will also bring up the C1, C2 and the CE in the picture. So you see that actually exact same circuit, exact same small signal model, but we also have the C1 now, C2 and the CE. And since CE is now in the picture, so it is not shorted, that means RE is also again back in the circuit. So we will now determine the lower cutoff frequency, and by using the short circuit time constant method. This is a very powerful method to determine the lower cutoff frequencies. You have also the open circuit time constant method, which is then used for the upper cutoff frequency analysis. So what I will do is consider the effect of one capacitor at a time, like actually superposition, and then we will then use those partial effects to determine the lower cutoff frequency. So I will first begin with the C1 and then disable the effect of the other two capacitors, and also disable the independent sources. So that means I look between the two nodes of my C1, I short my input because I will disable that, means shorting for the voltage source, and I also short the CE, I also short the C2. Okay, so what I see effectively, that is actually the question here. So this is again shorted, this is now shorted, so that means actually these two are parallel. Now what I see actually here between these two nodes of my C1, that is the question in place here. Determine the impedance seen by the capacitor C1. So it has actually the Ri here going to ground. So it's one hand is looking at Ri, the other end is looking at R1 parallel with R2 and parallel with this R pi. So the time constant associated with this capacitor C1 is then given by this expression, tau, time constant, C1, is C1 times the impedance looking or seen by this C1. That is this Z sub C1. In this case, it is actually simply Ri and plus the ZIB, because that was actually what we have used in our previous analysis. And ZIB was this R1 plus R1 and R2 and R pi in parallel was already calculated as 994.3 ohms. Take that here with this 100 and we can calculate now the time constant. So we can say 10 to the power minus 7, which is this 0.1 microfarads, times this 100 plus this 994.3, that is then 0.10943 milliseconds. So how do we go to the frequency? Now frequency is 1 over that time constant, so the pole frequency, so that is the definition of the pole frequency, is associated with this capacitor, is then given by 1 over this tau C1, so 1 over that expression, that will result in 9,138 radians per second. Now next we will do the similar operation for the capacitor C2, so we will look at the contribution of C2, only that, and we display again the input voltage and the other two capacitors will be shorted. Again, we'll look at between the two nodes here, and we short the CE and we short the C1. So what we need to do is again determine the impedance seen by the capacitor C2. Now, since we know that the early voltage is infinite, it means there's no resistor here between these two nodes. That is an open, and this is shorted, so this is then effectively grounded. And since this is shorted, this is actually 0 volts. That means at this node we have also 0 volts. Now, since we have 0 volts here, the V pi is 0. That means this current is also GM times this V pi, which is 0. That means this is 0. So we have also an open here. So effectively, the time constant of this capacitor C2 is then given by this expression where you see C2 and the impedance seen by the C2. And that is then RC plus RL effectively only. Why? Because this connection is completely opened. Thus we have this. So we have then 1 microfarad, so 10 to the power minus 6, and then 1000 plus 2000 from the RC and the load. We have then 3 milliseconds exactly. Now the pole frequency associated with this capacitor is then given by this formula, or this expression again, 1 over this tau C2, and that's then 333.3 radians per second. All right, the final one is the contribution by this capacitor CE only. Again, we disable the input and we now short the C1 and C2. So we look between these two nodes, so C1 and C2 goes. Again, we need to look at the situation seen by the capacitor CE. So what is the impedance seen by this capacitor? The time constant, again in general form, is shown here. So the capacitor itself times the impedance seen by this capacitor. In this case, it is the RE in parallel to this ZIE, and that is actually looking here up. Again, since we have an open circuit here, so this goes, and we have now R pi and this Ri, R1 and R2 effectively in parallel, which is in series with R pi actually here. So how do we determine that? Now, since we look from the emitter node or emitter branch into the base branch, we need to divide everything by beta plus 1. That is actually ZIE. So we see that. So it's R pi plus the parallel combination of these three resistors effectively, because this is ground. And that whole effect will be then also divided by the beta plus 1 in order to get to the correct expression. And that will be then in parallel with this RE, which is here 800 ohms. So let's calculate first this R1 and R2 and Ri in parallel. That's actually shown here. So 1 over that, 1 over that, 1 over that, each of them, and then also 1 over that is then given as 1 to the power minus 1. And when you now substitute the values, and you get here 99.3 ohms. So it's exactly or close to actually to 100 ohms, because these two are much larger than this Ri. So you can already approximate this by Ri, actually it's parallel combination. So our pi was already calculated, so it is 1065 ohms. So that's now shown here. So we substitute here everything and you get here very close to 4 ohms. So we get now a 4 ohms effectively looking up in parallel with this 800 ohms. So we can already say that this is also almost 4 ohms. Now more closely it is 3.98 ohms. Alright, now we have the necessary information, so we can go on and to calculate this time constant, which is then in this case 0.0398 milliseconds, which is in this case the lowest time constant in this case. So when we calculate now the pole frequency associated with this capacitor CE, again a similar form, 1 over that, and that will result in 25,119 radians per second. You see actually here now that we have the largest time constant, the smallest time constant and the largest pole frequency. Alright, let's make now the summary. We have the contribution by C1, C2 and the CE. So each of them, the formulas and also the results. We also have this and we have this. So we also have the values here from the associated impedances. You see here that we have here a little bit over the 25,000, here 9,100 and here almost 333. This is not really dominating in this case. Why? Because this is not much larger than the other two. This is of course much smaller, but this is still around 9,000 and this is 25,000. So you can say let's say the ratio here is almost 2.5. So it's not that much. So we can say we do not have a dominant pole in the circuit. So how do we work this out in these kind of situations? Now you can approximate, not an exact, but an approximate the lower cutoff frequency by add up these 3 contributions in these pole frequencies. Because when you have the poles close to each other, you get actually in a situation what we call the pole splitting. So it is not this is only dominating. If this was, for example, 900, for example, this is 33 or 333, this will really dominate, and we can say this is approximately also the lower cutoff frequency. But now we need to add them up, and then we come up to this 34,590 radians per second. If you now convert that into hertz, you just divide by 2 pi, you get here now almost 5.5 kilohertz. That's the result from our analysis using the separate contributions of each capacitor. Alright, let's now look at our simulation results. First we start with the DC analysis. This is the circuit and you see the nodes here, and this is the result we have found from the DC analysis. And this is the table where you see the detailed information for this circuit. You see here the IRC, which is the current flowing in this branch, which is here 7.088 milliamps, which is really close to what we have, so this is very nice. We also see here the current through the resistor RE, which is here 7.113 milliamps, which is also very close to what we have here. We also see here this 0.6, which is this resistor, this 0.6, which is the voltage at this node, which is 10.91 volts, and we have here 10.92 volts, so also very close to what we have. We also see is this voltage at node 1, that one is 6.38 volts, and we have 6.38 volts also, so very close to what we actually see here. So these are actually very nice confirmation of our calculations. Okay, let's also look at our simulation results for the Bode plot, because there we see the information really want from our design, or actually for this example. We see the circuit again. This is the Bode plot. You see directly this is a high-pass filter, but you see also some part of it that this is another pole which is activated. So it's not really a flat line which is going up. So it is actually a high slope here, and then the slope gets smaller and then flats out here in the higher frequencies. Now we have calculated our mid-band gain, or our maximum gain, which is minus 165, and in dB is 44.3 dB. We see here 44.3 dB, so this is a very nice result. The lower cutoff frequency we have calculated was 5,505 Hz, so almost 5.5 kHz. We see here 5.35 kHz, so small error. Again, why? Because we assume, or we actually use an approximation, which is of course not always perfectly valid, so maybe 95% or 80% of the time it is correct. In this case we see this a small error here. So it is still very nice with this confirmation in our calculations. So we can say we have achieved our goal, and we have verified our calculations in the SPICE simulations using the Bode plot here. Alright, it was our example considering the frequency response of the BJT amplifier having the coupling capacitors C1 and C2 and the CE as the bypass capacitor. We have used the short circuit time constant method to determine the contribution of each capacitor and then use the approximation or the approximate formula to calculate the lower cutoff frequency. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.